All right. Well, is the bus here? Should I wait? Yeah. Beautiful day. All right. So our final lecture. It's been good having you guys in class. Let's finish our discussion about how do we solve control problems where we have a final goal that we would like to achieve, and we want to get a control policy, which means we want to know what to do at every state, at every time point. So we have a cost per step defined by something that looks like this, a quadratic cost. And a motor cost. Okay, and so we said that we started the last time point and at the last time point our optimal policy at state x at time point p is the one that minimizes the cost per step. And so if this is our policy, if this is our cost per step, well, the best thing we can do that minimizes the cost per step is just nothing. And so the value of our state, if we were to have the optimum policy at the last time point, is just alpha of k evaluated at x of p, and with the action u star is equal to 0. So we minimize our cost per step to get the action, and then we apply that action, and then we get a value for that state. So then at time step k, the optimal policy is the one that minimizes the sum of your cost per step, given that you're starting at x, plus where are you going to go to, what's the value of the state that you're going to go to, given that you're at state x and you produce action k. So we assign a value to the state that we're going to go to. We just do it here, just like this. And then we find that command u that minimizes the sum. Once we find the command that minimizes the sum, then the value of our state at x of k is just the cost per step, given that you're at x of k and you perform the action pi star at x of k, plus the value of where you go to. So at every time point, we minimize a cost that is composed of cost per step and the value of the state that we're going to take to if we produce that action. Once we find the optimum action, then we assign a value to the current state that we're at, and which is the cost per step plus the value of the action when we go to. In this way, at every time point, at every state, we keep track of the best possible scenario from now on. And that gives us a value function. So we're going to use these equations now. These are the Bellman equations. That's the name of these equations that I just described, to solve problems. So I'm going to begin with the simple case of a dynamical system that has no noise. Okay, but before I do, let me ask you guys if you have a question about what we're going to be doing. So we're going to have a cost per step. We want to find out what's the best thing we can do, what's the best action to do at a function of state, regardless of the state we're in. What's the policy that we're going to have? And then solve the problem from the last time point to the first time point. Okay, so here's our dynamical system. Here's our cost per step. Okay, so at the last time point, the optimum action at time point x of p is the one that minimizes the cost per step at time point p. And the thing that minimizes this at time point p, you just use 0, so this is just 0. Don't have any action to do. If that was the action that I chose at time point p, then the value function for that state that I'm in, x, some location, at time point p is just this function evaluated with u being 0, which is just x of p transpose t of p x of p. Okay. So I'm going to show you that when we solve this problem, the value of any state at time point, any time point, is always going to be a quadratic function of a state if we have the optimum solution, if we have the optimum action. And in order to show you that, we're going to keep track of a variable. And that variable is this thing here that's going to quadratically affect state. So let me label the matrix W at time point P. Let's call this T at time point P. I'm going to show you, we're going to get an algorithm that's going to be a recursive way of computing what to do. So if this is my policy, then my action at time point P is some matrix G at time point P times x at time point P. Well, in this case, since my action is 0, G at time point P is just 0. That's my policy. It says, tell me where you're at, I'll tell you the action you produce at time point P. In this case, the gain of this system is 0. And so we're going to put that as our policy. Okay, so now what we want to do is compute what to do at time point P minus 1. So what we need is, what's the value function if I were to go to some time point x at time point P, x at time point P, given that I'm at P minus 1, and I perform some action u. So why do we need this? Because what I want to do is to find the optimum u, which is the cost per step plus the expected value of the state that I'm going to go to, given that I'm at current state. So I need to know what is this function here. Okay, so this function is just, given that I'm at x, p minus 1, and produce action u at p minus 1, then, well, it's going to take me to some place x that depends on the matrices A and B. So the value of that state is just this, but we're going to write it in terms of u of p minus 1. So it's going to be A times x of p minus 1 plus b times u of p minus 1. That's where it's going to take me, transpose, times the matrix T at time point P, that's the value of this function, times ax p minus 1 plus b u of p minus 1. Okay, so this tells me that if you produce action u and you start at time point x at p minus 1, here's where you're going to go to, x of p, and this is going to be the value of that state. you see that? Why? Because that's the value of the state x of p. That's what I just found under the optimum policy. Okay, so we're going to simplify this, add to it the cost per step, right? So we're going to, the expected value of this function, since it's just it's not a random variable, it's just itself, then we're going to add this to it, and then find its derivative with respect to u. That's going to be my optimum behavior at time point p minus 1. So let's multiply this through. So that's x of p minus 1 transpose A transpose t plus 2 times Okay, so I just multiplied the quadratic form through. Okay, so we have another component of our cost. That's the cost per step. So that's alpha at time point p minus 1 plus this v. Okay, so sum of these guys. We're going to have to minimize this sum with respect to u. Well, that's going to be equal to x of p minus 1 transpose t of p minus 1 x of p minus 1 plus u of p minus 1 transpose L u of p minus 1. That's my cost per step plus this term here. And my optimum policy at time point p minus 1 is the derivative of this function where we're trying to find the optimum u. So it's the sum of p minus 1 plus this v. All right, so we're going to find the derivative of this function with respect to the derivative of this plus this with respect to u. All right, so let's start with this. 2 times L u of p minus 1 plus this becomes 2 times b transpose t a x of p minus 1 plus this one, 2 times b transpose t of p b u of p minus 1. And that's the only ones where we have u's. So those are the derivatives that we care about. We set that equal to 0. Solve for u, and we get u star at p minus 1 is minus b transpose tp times B plus L minus 1 B transpose TP A x of P minus 1. So we get a function of x that says take this matrix, call it G, at time point P minus 1, multiplied by x, put a negative in front of it. That's the command you should produce when you find yourself at time point P minus 1 at position x. So that's our policy at time point P minus 1. Okay, so we have our policy now. Now what we have to do is assign value to the states at time point P minus 1. So just to be clear, what do we have? We have a policy at time point P, and we have value for states at time point P. We just computed U. We have a policy at time point P minus 1. So now what we need is that what's the value of my states under the optimum policy at time point P minus 1? How good are those states at time point P minus 1? Given that this is my policy. So this is this function where we're going to replace U with the command that we're going to generate. And when we replace U with that command G times X, we're going to get a function of just X. And what I'm going to show you is that that function is going to be a quadratic function of X. It's going to look just like this, X transpose times something times X, whereas this is going to be some new matrix W at time point P minus 1. So it's going to be a quadratic function of X. So basically, we will see that as we solve this problem step by step, we get a recipe of how to write each step in terms of its previous step. So, okay, so value function at time point P minus 1. It's this plus this plus this, where U is going to be replaced with the matrix G times X plus this guy here, alpha, the cost per step. That's my cost that I'm going to be incurring at that time point. So okay, so this value function is going to be X at time point P minus 1 transpose T of P minus 1 times X of P minus 1. So that's the first component of cost per step, plus the cost of the command, which was U transpose L times U. Well, I'm going to replace U with minus G times X. So U transpose is going to become X P minus 1 transpose G P minus 1 transpose times L times G P minus 1 times X P minus 1. So this is U transpose L times U. So the minus goes away because you got two minuses there. So this plus this is alpha at P minus 1, given that you're at X P minus 1 and you did the optimum command at P minus 1. Okay, so that's the first part of our value function. The second part is the value of the state that it takes us to. So that's going to be this term here. This term. These three terms here, where U now is replaced by G times X. All right, so that's going to be the place it takes X P minus 1 transpose A transpose WP, that's just T at time point P, A X of P minus 1. So this is the first term. This is this term here. where I replace t with that w. The second term is going to be that that it's going to have one u in it, 2 times 2 times u transpose times this. I'm going to replace u with g times x. So you get minus 2 x of p minus 1 transpose A transpose W P B times G of P minus 1 X of P minus 1. This is a scalar. Plus the final term, which has u squared in it. So that's going to be X of P minus 1t G of P minus 1t B transpose WP B G of P minus 1 X of P minus 1. Okay, so we can simplify this a little bit. So what was G, here's G here, is B transpose TB plus L minus 1. And which means that our term G P minus 1 transpose, this quadratic term here, times L plus, so this term here, plus this term down here, L plus B transpose WP times B times G P minus 1. So this plus this has x in it, x in it. This is the same, so we're just going to take L plus B transpose WPB. I just wrote it down here like this. So this is equal to G has B transpose TB plus L inverse in front of it. So this cancels this, and so what I get is G P minus 1 transpose B transpose WP transpose times A. All right, so now I can write the value function in a more simplified form at state time point P minus 1 as a quadratic form. So everywhere I have x transpose to the left, x to the right. Every one of these elements here has that term in it. So I can factor it out, x P minus 1 transpose times t at time point P minus 1 plus G at time point P minus 1 transpose B transpose W at time point P transpose A plus A transpose WP A minus 2BG P minus 1 all multiplied by x of P minus 1. It's a quadratic term in terms of x of P minus 1. So also this can be simplified, so we get x of P minus 1 transpose. This here can be simplified. We get x of P minus 1 transpose times t of P minus 1 minus A transpose WP B G P minus 1 plus A transpose WP times A x of P minus 1. So the value of our state at time point P minus 1 is also a quadratic function of x, and here's the matrix W at time point P minus 1. So V under the optimal policy at time point P minus 1 is x at time point P minus 1 times some matrix W times x of P minus 1. And here's that matrix. So I have now an algorithm. So let me summarize our algorithm of how to find one by one the solution to our problem. So at the last time point, my gain of my feedback policy is 0. My value function as a function of state at that time point is x of p transpose w of p times x of p, where w of p is this matrix T of p, which is given to me in the cost per step. And the action that I'm going to take at state x of p is minus g of p times x of p. This is the action that I'm going to take at that state. At time point any other, for example, g of p minus 1, my gain is L plus b transpose w of p times b inverse b transpose w of p transpose times a. And the action that I'm going to do, u star, at x of p minus 1 is minus g of p minus 1 times x of p minus 1. And the value of my state at time point p minus 1 is x at time point p minus 1 transpose times some matrix w p minus 1 at x of p minus 1, where this matrix w at p minus 1 is t at p minus 1 minus, it's here, this term here. I'm just going to rewrite it here. A transpose WP BG P minus 1 plus A transpose WP times A. And so you can just unfold this problem like this to P minus 2, P minus 3. So let's see how we do it. We start with the gain of 0. We assign a value function to our state based on some matrix W, which is equal to T of P. This is given to me because I have alpha at time point, any time point k is dependent on x transpose T at time point k times x plus u, LU, right? So T is given to me. I know what this is. I know W. I can assign the value to my state. And I have the policy in terms of the action that I'm going to produce. So in the time point P minus 1, I have a gain based on W at time point P. I can describe this gain for you. My action is to multiply that gain by my state at time point P minus 1. This is a feedback control law. It says, give me your state, I will give you the action. The value of that state is a quadratic function of x, which depends on this matrix W, P minus 1, which depends on T at P minus 1 plus W of P and the gain at P minus 1. So all of these are known to you. You can do this. And now you could do the same thing for, P minus 2. P minus 2 is going to have a gain at P minus 2, which is going to be exactly this, which is going to have a W of P minus 1 in it, and all these other terms. So actually, let me write it down for you just to be complete. So my gain at time point P minus 2 is L plus B transpose W at P minus 1 times B minus 1 B transpose W P minus 1 transpose times A. And my value at P minus 2 is X at P minus 2 transpose times some matrix W at P minus 2, X at P minus 2, and W at P minus 2 is T at P minus 2 minus A transpose W at P minus 1, BG P minus 2 plus A transpose W P minus 1. Sorry, this is P minus 2, P minus 1 times A. I just move the indexes by 1. And so I can unfold the problem to the very first state. All right, so let me stop to see the basic idea. The basic idea is to solve problems where you have an end goal and you have some cost you incur as you get closer to your end goal is as follows. You start as if you're at the end. You say, what's the best action now? That's the action that you produce. That assigns a value to every state because that's the cost per step evaluated given your action. Now that you have a value function for each state and the action that you should perform at each state, you move one step back and you say, for every state, given that I'm at some location, and this is the cost that I'm going to incur if I were to do something, where does it take me? What's the value of that state that it's going to take me? Value is just a way to keep track of all your costs. Find the best action. Once you do, then for the state that you're in at time point p minus 1, you also have a value function, which is the cost you're going to incur from now on, cost to go. And that's how you unfold the problem to get the very first time point. And at the end, what you end up with is to say, I'm starting at this location. I want to be at that location at some time point p, and I don't know what's going to happen to me as I move along because I could have perturbations, I can have noise in my system, but for every time point, I have a gain that tells me I have a policy that tells me, regardless of where I end up, what's the best action to do. So, as you produce the commands, as you change the system, you have a Kalman filter that can tell you where you should go on average. And so on the next time point, you know what to do because of what your state estimate is. You perform that action, you get feedback from the system that says you're actually at this location, you combine the two, you get an estimate of where you actually are, you do it again, and then you do it again. Okay, any questions about that? All right, so let's do it now for when we have noise. All right, so suppose we have a system that has noise in it. And so now if we have noise, then what we need to know is that what is the expected value of the state that we're going to go to if we were to perform some action. Okay, so we have a cost per step. All right, so as before, we started the last time point. We ask, what's the best thing we can do given that we find ourselves at time point P? So what's the policy that we're going to have at time point P for any state X? And so that's the policy that minimizes the cost per step. And so that's to do nothing, because that's you should be as small as possible to minimize the cost per step at time point P. What's the value of our state at time point P? That's just the value of cost per step. And so we have our W matrix that we say that's the weighting that we're going to assign to a states. Okay, so the next step is to say, what's the value of the state that we're going to go to at time point P, given that we're at time point P minus 1 and produce action U? Well, that value is given to us here. And so what's the x that we're going to go to, given that we're at p minus 1 and produce action u? Well, that's going to be a x of p minus 1 plus b u of p minus 1 plus some noise transpose wp times itself. Okay, so we multiply that through. Okay, so just a little bit of a longer, more tedious set of multiplications. So the only thing that's different about this than what we had before are these epsilon x's here. And so what we're interested in is finding the commands at x of p minus 1 that minimize now not the sum of this, but the expected value of it. So we want to find the u that minimizes the alpha, the cost per step, plus the value of the state that we're going to go to if we were to produce action u. So the cost per step is x of p minus 1 transpose t p minus 1, x of p minus 1, plus u of p minus 1 transpose L u of p minus 1. That's the cost per step, plus the expected value of this function that I just wrote. Okay, so what's the expected value of this function? Well, the expected value of any of these random variables here, epsilon, is 0, except this one here, where we have a quadratic form. So this is something that we have to think about. What is the expected value of this guy? So what we want to know is what's the expected value of epsilon x transpose w of p epsilon x. So this is not going to be 0. It's going to be something. So let's see if we can figure that out. So we're going to do a side step here. So let's look at what happens when we want to find expected value of a squared random variable. So for example, what's the expected value of x squared? Well, you know, what you do is that you say, well, what's the variance of x? Variance of x is expected value of x squared minus the expected value of x, quantity squared. And so that tells us that expected value of x squared is its variance plus its mean squared. So what if we have, this is if x is a scalar. So if x is a vector, then what we care about is what's the expected value of x transpose x. So this is now getting close to this. Well, in this case now, the variance of x is the expected value of x transpose, minus the expected value of x, the expected value of x transpose. So the expected value of the quantity x transpose x, that's equal, this is a scalar, right? So that's the expected value of the trace of the quantity x transpose. So this is our trick. So look, x transpose x is a scalar quantity. Trace of x transpose is a scalar quantity. And now I have a quantity here that looks like this. So because trace is a linear operator, I can take the trace out and put the expected value of x transpose in there. All right, so now this is equal to the trace, expected value of x transpose is the variance of x plus the expected value of x times the expected value of x transpose. So that tells me that the expected value of x transpose x is the trace of variance of x plus trace of the expected value of x, expected value of x transpose. That's just expected value of x transpose times expected value of x. So this is a useful identity that I can use now to go back and solve this problem up here. Okay, so let's write down what we had. We needed to know what's the expected value of this noise term and that's going to be equal to the expected value of the noise transpose WP, the expected value of the noise, so those are 0, plus the trace of WP times the variance of this epsilon x. Variance of my quantity, which means this is equal to 0 plus the trace of WP times Q, because epsilon x is normally distributed, which means 0 and variance Q. So, okay, why is this useful? Because you notice that there is no dependence on U. So this quantity, which appears in my thing that I want to minimize, it has this expected value of this quantity there, that doesn't depend on U. So if I go back now to my function, what I want to do is minimize sum of x transpose Tx plus U transpose Lu plus the expected value of this quantity. Well, the expected value of this quantity, this goes away, this goes away, this doesn't go away, but it has no U's in it. So that's fine. So this is exactly the problem that I just solved for you without noise. So adding noise to the problem did not change the solution, because the noise that I added did not depend on U. That was the key part of this. U, this epsilon is noisy, but there's no dependence of the noise on U. And so if that's true, whoa. Then my solution doesn't change. What that means is that my all the stuff that I just derived for you remain the same. So I have pi star, my optimum policy at time point p minus 1, remains exactly the same that I had, minus g of p minus 1 times x of p minus 1. And my value function at time point p minus 1 remains alpha at p minus 1, which is depends on x and u star, plus the expected value of v, where it goes to at time point p, given that at time point p minus 1, plus, comma, and I did action u, p minus 1, u star. So this is going to be the same as before. This is the same as before, except this expected value, same as before, except I now have the trace of WPQ as an additional term. So the more noise there is in the system, the greater cost there is in every step, but the optimum policy doesn't change. The gain of the feedback system doesn't change. So with these kinds of equations, you solve problems associated with this notion of having a cost per step, a goal that you want to achieve, and then getting a feedback control law that says how to do it. So these kinds of systems are robust to perturbations and so forth. So you're now ready to try these equations on a project, and so that's going to be your final. And your final is going to be, a large component of it is going to be using these equations. In addition to that, there's going to be two small problems that come from support vector machines and principal component analysis. That makes up the story. So you have a homework for today, and you had homework for Tuesday. That's due next Tuesday. We'll give you the project probably this weekend, and it'll be due I think May 17th, probably like 5 p.m. or something like that. So you'll have about 12 days or so to do that as well. And I'm hoping that with the project, you'll be able to bring all the pieces together as you work through the equations and try the system. Okay. Any questions, guys? Yeah.
So in the case of signal-dependent noise,
Yeah.
is it just that last term that you got then?
So with signal-dependent noise, both the gain change and the value function, because the noise system is going to have dependence on u, and so the derivatives are going to change because of the fact that, let's look at our equations here.
Just meant like the last epsilon transpose stuff.
No, so more than that will change. The reason is this. So this term here is going to have a u in it, because the noise in the system depends on the command u. This term is going to have a u in it. So all of these terms are going to have derivatives with respect to u.
But the expected value doesn't, I'm confused when you take the expected value.
Oh, right, I'm sorry. No, you're right, absolutely. The expected value of these is 0. This term,
Right, that's what I was saying.
yeah, I apologize, yeah. When it's squared, then you're going to have u squared in it. Yeah, good point. Yeah, it's going to have a variance that matters, right? So then this term here, this expected value is going to have a trace of a variance in it, and that variance depends on u, and so the derivative of it depends on u. Yeah, not its expected value. Okay. Good. Thank you so much. Good to have had you. I hope you have a good summer. And if I can help you in any way, just let me know. Thank you so much.